Morning, everyone. So yesterday we started looking at what's referred to as a rate expression or a rate law. Essentially, it's a mathematical function that compares the speed of a reaction. It's proportional through a rate constant k, and the k is everything except for changing in concentration. So I'm just going to give you a quick warm-up question so you can practice that here. Let's see how we do. So I'm going to give you a reaction here. Let's say it's 2D reacts with E. This one here becomes F, right? That's my reaction. What I want you to do here just for practice, I want you to state the rate law, state the rate expression for this equation, and then B, I'm going to do the hard part for you. I'm going to have done the method of initial rates, essentially setting up my experiments, just doubling one chemical and leaving all the other chemicals constant so that I can first find the order. If I know all the unknowns, I can always ask you to calculate for one missing one. So I'm going to say given the reaction is first order in D and third order in E, calculate K, which is the rate constant. Calculate K when the concentration of D is the same as concentration of E, just to save us a little bit of writing here. The concentration of both is 1.3 times 10 to the negative 2 mole per dm negative 2. And the rate, the actual speed of the reaction at this condition, the rate is 3.75 times 10 to the negative 5. A funny set of units here, mole per dm negative 3, and seconds minus 1. Right? So again, I encourage you just to pause the video, try it out for yourself, and then you can check your work with me afterwards. Assuming you've done that here, for the rate expression, in general, we're looking at rate equals some proportionality constant k, which we're going to solve in B. It's going to depend only on the reactants. So the reactants here in our case, there are D and E. While it is tempting, D has a coefficient of 2 and E has a coefficient of 3, those coefficients in general, they're not the powers, they're not the orders. We can only determine these orders. I'm going to call it X and Y for now. We can only determine these orders here. Orders can only be determined experimentally. You have to have run an experiment to actually get these numbers. And in fact, they've done this for you here. They've done the method of initial rates here. They found that we're actually first order in D. They found that X is actually 1. Oh, that's fine. It doesn't actually match up with D. We'll see a little bit in this lesson why that's the case. And then E is actually third order. Usually the order doesn't get to be overall like way too big, but you get the idea. 0 order all the way to 3 order here. You'll notice as well, when I wrote out this rate law here, I couldn't care less what F is. Not only did I matter what number of the coefficient there is, F is a product. My reaction rate here only needs D's and E's to collide together, good energy, good geometry. It really couldn't care less what the products formed are. So now we have a sort of standard rate law here. I actually know most of the numbers. You can try rearranging it for yourself. So if I'm looking for K in this experiment, I'm going to go the K is equal to the actual rate, the actual speed at this point. I'm going to divide D to the power 1 and E to the power 3. They've given me those numbers there. And this will end up giving you K. Part of the hard part, numerically, is not too hard. Just do the division, plug in the numbers. But part of the hard part is to write the appropriate units. K basically has to have the right units. It can kill off all the units on the concentration and leave you with the right unit for a rate. So I can actually do that part first. My rate, I know in general, remember rate has to be, it's an increase in concentration of products over change in time or decrease in reactants. My rate is expressed molar per second. I now have the orders, so I now have this one is molar to the power 1. That gives you already one of the molars. This one is now molar cubed. That means my rate constant would actually need to have, in total I have a molar to the power 4. I only want molar to the power 1. So I need 3 powers of molar down here, and I want a seconds on the bottom. So for this set of combination, for this overall being 4, the order has to be 1 over molar cube seconds. So let's plug our way through. people always get confused. What do you mean rate? Rate is the speed at this point. So the rate is 3.75 times 10 to the negative 5. Is a funny set of units there. We already worked out the units earlier. D and E coincidentally happen to be the same number. So even if they weren't, I just plug them in here. Pretty much once you know the powers, you're home free. You can just plug your way through. Just a little bit of calculator work here. Let's find out what a rate actually is. 3.75 e negative 5 divided by 1.35 e negative 2 divided 1.35 e negative 2. That I need to divide that 3 times. And I'm getting the rate constant here as 1130. And our units, like we said, it's going to be 1 over molar cubed second. Let's see if I can clean that up a little bit. That means it would be molar to the negative 3, seconds to the negative 1. IB doesn't like you using molar here, so you're actually going to punch in there. Well, molar means mole per decimeter cube. This is to the power negative 3. So what you're going to do, the negative means you're going to flip the fraction over. It's going to be decimeter on top. 3 to the power 3 is going to be decimeter 9, and then mole to the 3, and then we're going to have seconds to the minus 1. So that's also on the bottom here. And now you can actually write it all in one long row here. You can say, well, it's going to be 1130 decimeter 9, a mole to a negative 3, and a seconds to the minus 1. And that's how you just write it in one long row there. I would do exactly that work to figure out the units for K. Punching in the numbers weren't all that bad. Just to finish off from yesterday here and looking at these orders, what do they actually mean for the graph? You can flip over to our notes package here. We can actually plot this graphically. Up to this point, we've just been plotting, well, change in mass versus change in time, change in concentration versus change in time. I've actually been measuring the continuous rate at which chemicals are released. In this case here, there's two ways I can also plot the graph. The order of reaction can be deduced from a graph if I plot the initial rate, the actual speed, versus the initial starting concentration. So for example, when I'm zero order in a certain chemical, there is no change to rate when your concentration changes. Right? So how do we plot that? The rate is set by just sort of looking at the y-axis here. This is the rate. I don't care what your concentration is. I don't care whether you're low concentration or high concentration. If we are that to the power 0, this rate here is actually going to go straight across. So if I plot it in this fashion here, zero order, the speed of reaction actually doesn't care what the starting concentration actually is. Right? What if it's first order? First order means that the rate is proportional to the concentration. So when I'm high concentration, the rate is high. When I'm low concentration, the rate is low. So high concentration, I'm starting out high. As the concentration steadily drops, the initial speed is less, initial speed is less. For a first order reaction, we actually have a line that just goes up linearly. So this one here is going to be first order. And then for second order here, it's just also going to definitely be changing relative to the concentration, but the rate is actually going to be proportional to this squared. So when the concentration is doubled, the rate multiplies, or it's increased by a factor by 4, right? So what's going to happen here is I'm starting off, sorry, these should go through the y-intercept with 0 here. So these should go through 0. Basically, yes, this rate here is also going to depend on the concentration, but it's going to depend on the square of the concentration. For starters here, it's not going to rise that fast. But as I get a little bit higher, the rate is going to increase quite a bit more dramatically because the rate is going to be proportional through whatever chemical squared. So even though the A may be steadily rising, the square of it is going to climb a little bit faster. So this curve here is going to end up being the second order curve. And in a similar fashion, you can get third order and whatnot. Usually we don't get too far beyond that. So that's one way of doing it here, but this plots it against the starting concentration. As the concentration steadily changes, this graph is actually showing us how the speed is actually going to change. Another way we can demonstrate this order stuff here graphically is we can plot it really against our earlier graphs here, concentration against time. Really think of sort of rate is change in the product concentration versus time, or change in the reactant concentration dropping with time. As we just sort of say this to ourselves here, when my concentration is 100%, when I'm a high concentration, this is plotting against time. Remember, the slope is going to be my rate. So this is given my slope of this curve here. You'll notice that my slant here stays constant. When I was at really, really concentrated, the slope is constant. A little bit later, right, I would use up some of the reactants, the slope is constant. Slope is constant. Because in this case here, the slope is constant. You can use the terminology here. We have a constant gradient. Right? Gradient is another fancy word for slope here. This one there implies we are actually zero order in this chemical. So it's like rate was supposed to be proportional through this chemical, but because it's to the power 0, this chemical can be whatever it wants, but it's going to be to the power 0. What's the unit for rate here? Well, the rate unit here was supposed to be molar per second. Well, if I did plot in the proportionality constant, if I did k here, if that one there became a 0, I'm just left with the rate being k. That means the units for k needs to be molar per second. Now, just sort of tracking through the slopes here. At the beginning, when my concentration is high, we actually have a really steep slope. And then we gradually get more and more shallow because I have less particles. There's not as many collisions that are going to happen with the right geometry. There's less particles with the right amount of energy. All that comes back again. This one here is actually plotting for you a first order graph. So for a first order graph, we're looking like something like a rate is proportional k through a to the power 1. In this case, again, just bank on the fact rate has to be in units molar per second. Oh, great. A already has the units molar per second. That means k here actually doesn't need to have any units. So in this case here, so k, it's still going to have a value, but it's going to have no units because it already has the molar per second that it needs from earlier. Second order graph here would also depend on concentration. At first, the steep is very, very dramatic. The speed changes really, really quickly at first, but then as I step forward in time here, it actually gets less and less. So in this case here, it's actually dropping quicker at the beginning. That's the second order reaction. The rate is actually proportional through whatever chemical squared. Again, just a comment on units here. We can see when molar per second, this one's actually going to already have a molar squared. What unit does k have to get rid of whatever it doesn't want from A and pick up the molar per second? I can keep one of the molars, so I just want to divide by one of the molars. I need to pick up a seconds, and therefore that's my units for k. So my units here would be molars to the -1, seconds to the -1, and then you can do that same practice. The molar is mole per decimeter cube, all to the -1, seconds to the -1. So in total, you should be able to clean that up for me here and make that decimeter, mole per, this is, I already put the power, so dm cubed like that. So decimeter to the -3, mole to the -1, and then seconds to the -1 there. Oh, sorry, decimeter, just positive 1, positive 3. All right, so the units of k here, it just needs to kill off whatever concentration units left behind and leave it with a molar per second. In fact, we're going to come back to this. You might recognize this notation. T half is actually a half-life. So if I wait exactly half-life, I drop from a concentration of 100 to 50. Now that I have half the sample left, if you wait the same amount of time, I actually am 25. So for having a constant half-life, that's actually a first order relationship. So constant half-life. Right, so if you look back in the radioactive decay formula there, it will always be a constant there. Today I'm going to introduce to you one of the last topics here, which is called reaction mechanism. And then tomorrow we'll come back and take another look at this K constant. We've been saying it depends on temperature. How do I actually find out what K is, and how do I actually figure out what how does temperature actually impact K? In terms of this reaction mechanism stuff here, I always think of a reaction mechanism. A reaction mechanism, actually they list the definition for you here. A reaction mechanism is the actual sequence of steps. We're going to call each of these steps here an elementary process or an elementary reaction. Elementary means the basic. Elementary actual sequence of steps by which the overall reaction occurs. So let's think through an analogy here. Let's say our project is to build a house, right? So if you want to build a house, you don't just suddenly, okay, huzzah, there's your house, right? You actually build it in steps. You might lay the foundation first. That's step number 1. You might frame the building in step number 2, right? Make sure it's structurally sound. And then you put on the roof as the last step here. Your overall project maybe just build the house. But basically what we're doing here is we're saying, what are the actual steps that you need to do to actually get this overall, what's referred to as a net reaction? So simple reactions, as we have seen, can proceed in one step. essentially A2 and B2, let's actually write this down in words here. So A2 and B2, right, those should be diatomic. So A2 and B2, these guys here just have to collide. Collision theory says they have to interact. They have to collide with, again, our two features here. They have to collide with sufficient energy. They have to be able to overcome that activation barrier, and they have to collide with a favorable geometry. They have to collide with the correct angle of hit. If they're not moving fast enough here, by the time they trade in potential, they haven't quite made it up to activate complex, they just come right back down, unsuccessful collision, right? In this case here, we refer to this as a two-particle collision, right? Because as you can see, it is just one thing colliding with another. Not too hard, because I just need two particles to run into each other. But I've seen more complicated things like, for example, 4 HBRs and 1 O2 here. This is actually a 5-particle collision. Now, what makes this one here so hard? We still have always the same requirements. We need to collide hard enough, right? It needs to have sufficient energy. We also need to collide with a favorable geometry with a correct angle coming into it. What's so hard about a 5-particle collision is we need 5 independent particles. I don't need 2 particles to collide first or 3 particles to collide. I need all of them to happen to hit the same location in space. So not very likely. They need to arrive all at the same time. And not only that, they don't just need to luck out and collide all at once. They need to collide with all the right energies. So even if I had 3 of these particles as fast moving and 2 of them unfortunately were slow moving here, not enough energy here, no successful collision. So the chances of a more complicated collision, you can make a note to yourself here. Collision between 5 atoms, not very likely for 5 particles to be at the same spot at the same time, right? And even if this happened, right? Oh, they're gases, they're traveling around really fast. Even if one time they didn't collide, right? Oh, they might happen, right? But when they collide, they still have these 2 requirements. If they aren't colliding with the right energy or the right geometry, they won't actually be able to react. So what that should actually tell you here is not only is this reaction here going to be extremely slow, it should be actually impossible, right? If these 5 particles have so much difficulty being at the same spot at the same time with, again, the right energy, with the minimum energy, with the right geometry here, sort of the plot thickens against it here. It's getting harder and harder for this reaction to occur. However, reactions like this do happen. How? So what I'm actually saying here is we actually have a reaction mechanism. Basically, this reaction here, we can call this the overall reaction or the net reaction. This reaction is like me telling you, let's build the house. This is the overall, this is what it's going to look like. But building a house actually takes place in multiple different steps. What you need to do is actually do a couple individual reactions. No, you're not going to need to propose a mechanism from scratch. It's not like, oh, propose a 10-step way to build this house. But if they list for you most of the steps here, you should be able to sort of solve your way through the puzzle, and you should be able to figure out how the house was being built. So reaction mechanisms are made up of a series of intermediate, they're called elementary steps. We can call them intermediate steps, or you can call them intermediate reactions. In fact, even though the building a house was a reaction, each of these steps, basic as it is also a mini reaction as well. Each of these ones here will have their own energy barrier. You can make that note to yourself. Each of these steps, each step has its own activation barrier, right? There's always an energy requirement. But as we're going to see in these steps here, it's a little bit easier than having 5 particles collide all at once. So let's take a look at what's proposed here. They give us, this time, it's a 3-step pathway. Step number 1, I don't need all 5 particles to collide all at the same location. Let's just get an HBr to collide with an O2. Great. This one here is only a 2-particle collision, a lot more likely to come in with the right energy, the right geometry. This ends up producing a guy called Huber. All right. Step number 2, also a 2-particle collision. Also take another fresh HBr, collide it with the Huber, and we get 2 Hubers, right? Also very likely. Step number 3, again, just using this argument here, probably not very likely, right? 2-particle and 2-particle, I need 4 particles all colliding with the right energy, with the right geometry. If I really did this in detail, probably step 3 needs to be broken up into a bunch of mini steps, just to avoid some of the complexity, they just sort of kept that step together. And in fact, experimentally, again, a lot of this rate stuff here, in trying to find the orders reaction, you have to run an experiment. You can't just look at the stoichiometric coefficients here. Experimentally, one of these steps here is actually seen to be the slowest step. And it's not the step that I would have imagined. The slowest step is given a special name. This guy here is called the rate determining step, or you can say RDS for short. If it's a slow step, we expect this one here, even though every step has its own activation barrier, we expect this step here to have the highest barrier. These particles really need to be zipping away really, really quickly. This is the biggest hill to surmount. Once they've done this, the other two are relatively easy. What makes this barrier here so high? It could be the number of particles colliding, but in this case here we see, wait, why is a 2-particle collision actually slower than a 4-particle? In this case here, it may be possibly the bonds I'm trying to break are a little bit stronger. Maybe I have stronger bonds. Maybe I have more bonds that I try to break. All of those things here might amount to the first step being slower. All that to say, you can't just look generally and be like, oh, 4-particle definitely slow, right? Why is this called the rate determining step? Our goal is to do the overall. Our goal is to do step 1, 2, 3. But because step 1 is so slow, it's almost like step 2 and step 3 are just waiting. Fine, are you done yet? Are you done yet, right? Let's use sort of, let's say we worked at McDonald's here. Let's say step 1 was cooking the burgers, step 2 was assembling the burgers, and step 3 is delivering the burgers. Cooking always takes the longest time. We need to wait for a free stove. We have a limited number of chefs in the kitchen, things like that. That's a very slow step. By the time the burgers actually cook, you pass it on to people assembling. The assembly people are right away, oh great, assemble the burger, deliver, send it off, done, right? So your overall sort of business of getting the burgers out to people are limited by the slowest step. If you were going to hire more people, more workers, you would hire them always for the slowest step, because if you can speed up that slowest step here, you can speed up your overall reaction. Or, for example, you can buy more stoves, right? If I have more stoves to play around with, I can cook more patties, more burgers. That will speed up the overall production. Let's just make sure that my overall net reaction is still the same. Even though these ones here are individually reactants in their own individual elementary processes, all of these guys here should go on the left. All of these guys on the right should go on the right, except we actually see that some of the chemicals actually cancel out. For example, we actually produce the Huber in step number 1. We actually use up a Huber in step number 2. Instead of writing Huber on the left and Huber on the right, that cancels out. Don't write either of them. There's another one that's like this. It's formed and then it's consumed. I make a 2-Huber. I make 2-Huber and I use a 2-Huber. Those also don't appear in the overall. So what is actually the overall? What were really the reactions? What were really the products in this experiment? In total, I have 4 HBRs that are reacting. I'm writing for you the net reaction. They can ask you for this overall given these many steps here. 4 HBr reacts to the O2. That was our initial 5-particle collision, and this one ends up generating 2 waters and 2 Br2. This should feel reminiscent of sort of Hess's law here. We have a net reaction and overall. Basically, it didn't matter if I did the direct pathway or the 3-step pathway in, it still gets me from the same start to the same finish. A couple other notes here I already indicated to you. Why does it matter that step 1 is so slow? We already talked about this one here. The slowest step, called the rate determining step, the RDS determines the speed of the overall reaction. Again, the people waiting around to assemble the burgers and pass out the burgers are just waiting on the burgers to cook, right? If you can somehow cook the burgers faster, we can overall do this net reaction much faster. So that's the one I would expect to have the highest energy hill. So if I plotted this on a potential energy diagram here, I plotted against time, let's say. Even though I do have one overall reaction, I have one overall job, this is broken up into 3 separate reactions. Each step has its own energy barrier. The first one, which they told me is slow, I had said high energy barrier. Really big activation barrier for the beginning step here, EA1. And then afterwards, step number 2 is relatively easy. EA2 is a little bit low. EA3 also a little bit low. I don't know overall whether we're exo or endo. That depends on the reaction. But definitely here, the one with the biggest hill is always the slowest step. If you can somehow get over that hill, the other hills are pretty easy to go through. So make sure you know that name there. rate determining step. It's the step that determines the rate. Now there's also 2 other little definitions we can do here. What about the Huber and the Hober? They got made and they got used up, but they didn't appear overall. We give them a special name here. The Huber, I'm going to throw in the Hober as well, and the Hober. Sure, I produced 2 of them and I used up 2 of them. These 2 are known as reaction intermediates. That's the full name, or you can just call them intermediates. Huber and Hober are reaction intermediates that cancel out before the overall reaction. So basically, why don't they show up either on the left side or the right side? I'm not purposely putting Huber in. I'm not purposely using them up. They were created in an early step. They're used up in a later step. Because they disappeared before the net reaction was done, we refer to them as intermediates. I want you to be really careful, though. The intermediates, for example, Huber, was the product of step number 1. Huber would actually be sitting here. Huber is a chemical. You can isolate it, right? It's stable, right? It's low energy. Huber is not a activated complex. An activated complex here is actually at the top of the hill. Activated complex, we use that terminology here. Activated complex was what you needed for that minimum energy requirement. The activated complex is referred to as a transition state, right? Really high energy, really temporary molecule here. Activated complex, this is the transition state. This molecule here in between cannot be isolated. This one here is too unstable. This is in the process of rearranging bonds. The Huber has already rearranged its bonds. The Huber has already formed. It's just that overall, because step 1 isn't the overall, it's not the entire reaction. Overall, the Huber ends up canceling out. So anything that is made in an early step and used up in a later step is referred to as an intermediate. So let's have a look at that chloride ozone mechanism again. So when you look at this, they're going to ask you for what's the net reaction, right? All right, so net reaction pretty easy. Anything on the left goes on the left side. Anything on the right goes on the right side. I notice that I create ClO radical in the first step. The ClO radical gets used up in this step. That one cancels out. I also see chlorine. We had already called it a catalyst. Chlorine as a radical goes in. Chlorine as a catalyst comes out. That also cancels out. So the net reaction this time, based on these steps here, an O3 runs into an O and it becomes 2 oxygens. One formed in step 1, one formed in step 2. I've been able to get the net reaction or the overall reaction. In this case here, just terminology-wise here, for an intermediate, again, just for clarity here, an intermediate is formed early and used later. So it's formed in some early step, used up later. That would be like ClO, right? ClO was not something I had put in. It just came out of step 1 and it got used up and basically it's gone. It does not need to be the subsequent step. It doesn't need to be the step right after. This could be a 10-step mechanism. As it gets used up in step 9, it's still an intermediate. But what about, why do we call chlorine, why is this not an intermediate? Now you see chlorine here is actually something I purposely put in. Previously it was just ozone. Ozone was trying to collide with oxygen. It was really, really hard for that to happen. What I did is I added chlorine, right? This is not something that was created. I added it, but it also disappeared overall because the catalyst ends up getting regenerated later on. So we refer to this here as a catalyst. A catalyst is added early in some step of the mechanism and regenerated. It's reformed later. So it's not like the catalyst can somehow just magically, oh, go faster, go faster. The catalyst actually does enter the reaction, but it's just somewhere along the way, somewhere along the mechanism, it actually gets regenerated. It's not consumed overall. So you may have remember that for catalysts here, it's not consumed overall. Now, if you think back to our definition for a catalyst here, so chloride is our catalyst, we start off with a potential energy diagram. Again, I'm not sure whether this mechanism is endothermic or exothermic. Let's assume that's exothermic for now. So reactants and products. At first, the net reaction was just, I hope an ozone runs into an oxygen. This reaction happens to be really slow at the beginning. Really slow means really, really high barrier. So in this case here, the EA for the uncatalyzed path, it's almost impossible for the ozone and the oxygen radical here to be fast enough to get over the energy hill. How does a catalyst work? By adding a catalyst, we wrote this down earlier, A catalyst, it provides an alternate mechanism. It provides an alternate pathway to get from start to finish. And that pathway turns out to be an easier pathway. We can't just look in terms of numbers like, oh, one step is easier than two step. We have to look at the actual steps themselves. In this case here, by separating the mechanism into a two-step pathway, once I put the presence of chloride in there, I've catalyzed the reaction. I let the chloride first destroy the ozone. That happens first, and then step 2 occurs. I've broken up reactant. I've actually run it through 2 reactions. And basically, through this pathway here, it's like a detour. And you actually see that even if you look, both of these actually have an EA. But the EA for the catalyzed path is actually lower. I'm actually making it easier for the reaction to occur. It's like, let's say you set off to go home one day from the school. You notice, hey, there's a lot of construction on the way you normally walk home. There's a detour. It may be a longer pathway, but it's nice and flat and nice and paved for you here. You're going to decide to take the detour. You're still going to get from the same start to the same finish, but it's much easier for you. So therefore, it overall is a faster reaction. So it provides an alternate mechanism, an alternate pathway. The key here is with a lower activation energy, with an easier pathway. Right? And again, it's not necessarily the number of steps. Sometimes a 2-step pathway is harder than a 1-step pathway, but overall, it's actually looking at the pathway itself. It's actually an easier way to go about. What they really always like asking for a catalyst question, you are still getting from the same start to the same finish. If I just plotted the delta H overall, the delta H is actually unchanged. So the delta H is unchanged because it's the same overall reaction, right? So just look out for that one there, right? That's the difference between a catalyst and a catalyzed path and a uncatalyzed pathway. So what they do for you, I already sort of sketched it out here, this Huber and Hober reaction. Every elementary process by itself is actually its own step. So if you just sort of match it up for me here, this is totally hypothetical. I don't know if actually it's really 3 steps, but based on what's proposed here, I start off with step 1, HBr and O2. The first energy hill was the highest because they said the first one was the rate determining step. So EA is really, really large. Right, so that's step 1. We end up producing our Huber. For our Huber, we end up running into another HBr here. There's another smaller hill. Again, I don't know necessarily is this exo or endo, but overall this takes 3 steps. So we are 3rd step here. Maybe this one drops way down, right? So we have our 2-Hober here. The 2-Hober is actually a product. It actually forms, right? So you can actually isolate that. You can actually stop it there if you want. At that point there, we run it into the last 2 HBRs, and then eventually we end up with 2 H2Os and 2 Br2. We are still getting from the same start to the same finish. The overall delta H is unchanged. It's just we took a different pathway. And a catalyst here, in comparison, a catalyst would always have an easier pathway. Okay? So let's just finalize this with a few other comments here. Despite all the different kinds of chemical reactions that can exist, like the one that we just looked at, there are actually only 2 kinds of basic steps, 2 kinds of basic processes. One of them is referred to as a unimolecular process. A unimolecular, also called molecularity 1, essentially this involves one species breaking into any number of products, 3 products, 5 products, okay? One thing, right? So A just breaking off to become B and C. At this point here, we're talking at a really, really theoretical level, right? I don't know how the reaction actually occurs. But theoretically, what I can imagine is I can have something smushed together, and one thing is actually breaking it up to become more than one thing. If I try to do a rate law for here, it would be the rate is actually, let's say it's through A, it's just the reactant, but because it's just the only reactant, this A here is to the power 1. Now, I've been telling you here, you can't find the order just from the stoichiometry. You can in this case because we're looking at such a zoomed in. This is already looking really microscopic. This is actually referring to what the particles themselves are doing. Well, this particle here is breaking up. Right now here it's 1 particle, so A to the power 1. So I would say in general, don't do the order from the stoichiometry. This is an exception here. This is the one time it works. and we're going to see in the next step here, for a bimolecular step, theoretically, it's going to be basically a two-particle collision. They come in with good energy, good geometry here. Basically what we have, the molecularity 2 means you have two species colliding or combining into a product. So in that case there, we may have maybe two of the same species. Maybe A plus A ends up becoming B. Or you can have something like A plus B ends up becoming C. Both of those involve two-particle collisions, right? It just depends on sort of what type of material. So if you want to look at the rate law then, you can say, again, theoretically, if really it is an A colliding with A and those are your only reactants, it would be second order in A because it depends on A and A. Or if they're different, maybe it's first order in A and first order in B, right? These are actually theoretically the only collisions that I have. What about the 5-particle collision I had? Well, the 5-particle, I can't just look at the stoichiometric coefficients. I can't just be like, oh, HBr is to the power 4 and O2 is power 1, because it's actually not all 5 colliding all at once. In fact, it's just these two that collide first, and it's just these two that collide first. And by the time you get to the overall, maybe the overall order has changed. So still, as a general rule, do not find the order from the stoichiometry. We can only do this very theoretically, and we're going to walk through a few examples of what this sort of implies later on. Termolecular step is possible. Again, a 3-particle collision here, all getting to the same spot in space, all coming with the right energy, right geometry. I think they've done the math of this here. It's about 1,000 times less likely, but it is technically possible, right? We're talking theoretically anyways. So that's what they call the molecularity. And molecularity always is we're interested in for the slowest step, which is the rate determining step, right? So here's what's interesting about the next question. We have a balanced equation, and we'll end off with this. We have a balanced equation that says 2A and B becomes C and D, right? This one here is the stoichiometry. So when I'm trying to write the rate law, when I'm trying to do the rate is equal to K, A to the X, B to the Y, in general, don't take these orders from the stoichiometric coefficients because I don't really know, is it really 2 A's that actually collide with a B all at once? If it were, I can do A squared B1. They're actually going to propose over the next page or so, they're going to propose 5 different ways. These are all possible mechanisms, possible ways I can get from start to finish. So this is how it really could happen, theoretically. Well, to get 2A and B to collide, maybe 1A and 1B collides first in a bimolecular reaction. They form an X and a C, and then A reacts with that X, that intermediate, and reacts to become D. Let's just make sure that it's still the overall. Well, the X itself cancels out. It was formed and then used up. X is an intermediate. That cancels out. Overall, we're going to have, well, 2 A's went into the reaction with B, and we get a C and D. Great. Maybe this overall reaction happened in this fashion here. Now, for a mechanism that took place in multiple steps, one of them was a slow step. This step, no matter how fast it is, going to control the speed of the overall production. So when I do this here, because I have proposed the mechanism, I'm actually seeing what is physically colliding with which. I can actually use the coefficients in this theoretical equation, and I can try to do the rate law from this expression. The rate law, in this case, is going to be through a proportionality constant k, A to the power 1 and B to the power 1. Right? In general, you can't do this. In general, the stoichiometric coefficients were actually a 2 and a 1. In fact, it's only the slow step that's actually limiting how fast the production is. Notice experimentally, maybe it's just to the power 1 to the power 1, because theoretically, it's just 1A collides with 1B. All right? Let's look at another mechanism. Let's just guarantee that, 3-step pathway here. Let's make sure that this is still the same reaction. So the X cancels out, the Y cancels out, those are intermediates. In total, I have 2 A's, they collide with a B. Yeah, we still get C and D. So maybe my balance equation, which is unchanged, right, where I couldn't borrow the stoichiometric coefficients to get the order, maybe it actually takes place in 3 steps, and actually the slowest step, they have to give you this. The slowest step is not always step number 1, but the slowest step here is actually the first step, and step number 1 actually involves B just separating to becoming X, something like that. So in that case there, we're actually going to have rate is equal to K, B to the power 1. So if realistically it really is a B transforms itself into X first, it's just depending on the one chemical B, it is to the order 1 for B. But again, if I have this rate order, that was not borrowed from the balance coefficients. The balance coefficient would have actually said a squared. In fact, if I really wanted to put it in, we actually figured out from this proposed mechanism in part B, a is actually to the power of 0. Hopefully this helps explain to you how come some things are actually to the power of 0. Don't I really need a to actually collide? It's possible that the a actually enters some of these faster steps. Using the McDonald's analogy again, our passing out of burgers, getting the burgers to the people that order them are not limited by a. So yes, while in the background, a is needed to collide, the slowest step that's actually determining the rate may be only depending on b. So in this proposed mechanism here, when I say it's 0 order in a, while a is needed to collide with good energy and good geometry, it's not in the RDS, it's not in the rate determining step, it's not in the slowest step, it participates in some other collision, two-particle collision, yada yada, or overall rate just depends on the slowest step. It's not in the RDS, so does not largely, it will have a little bit impact, but does not largely impact the overall rate. And that's why we can actually have a 0 order reaction, and that's why we can't just take the, let's just take the stoichiometric coefficients and put them into the powers. That's why we can't do that, because I need to really know how the collisions are actually happening. Right? So let me just do one more with you here. Let's go C. Basically, let's just emphasize, make sure we have the same reaction. A2 cancels out. This is an intermediate, right? It's still 2A and B. Notice that our overall reaction is unchanged, right? However, in this case here, they tell you the slow step. I want to say something like the rate. Okay, fine. A and A have to collide to become A2. My slow step is going to be A and A, right? There we go. So first order in A, first order in A, or you can write that as A squared. Sorry, I actually realized I wanted to do the second one for you here. So for that one there, no real twist to it there. That's just C. I wanted to do D with you here. So D, in a similar fashion here, two A's form an A2. That's an intermediate. But this time, the difference between proposal number 4 and proposal number 5 is the fact that the second step is actually the slowest step. So if you try to do D here, you would say the rate, it's just the A2 to the order 1 needs to collide with the B to the power 1. In general, we don't like writing the rate relative to an intermediate. So just like we did in A, how come we had this intermediate? The intermediate actually came out of A times A, 2 A's multiplied. So I can actually sub in A and A. So therefore, in this situation for proposal D, we actually have A second order, B to the first order. Right? So I'll allow you to finish off this one here. Double check that the net reaction is still the same. Sorry, this should be K's for all these ones here. But basically, at this theoretical level, if this is really the things that are colliding together, we can use the coefficients for these elementary processes. The order only matches the stoichiometry for these theoretical, right? I don't really know if this is the actual way it happens for these theoretical elementary processes. If these are really the molecularities of the solution, if these are really the things that are colliding, I can borrow those coefficients. But you see that we actually have proposed 5 mechanisms. All these rate orders are different for the overall mechanism because I don't know how this net reaction actually occurs. I can't, in general, take these stoichiometric coefficients and put them in the order. Right? So play around with some of those questions there. There's some questions even afterwards on the next page over. Right? If you have any questions, just let me know. Thanks, guys.